Okay, again, here's our situation. We have mass M1, 100 grams, sitting here, and a mass M2, 70 grams, sitting out here. 3 centimeters between the two masses. What we want to do is we want to calculate the gravitational field at this point due to this mass. Because this mass is going to respond to that gravitational field. Gravitational field, of course, is acceleration, and it'll either accelerate toward the other mass or it'll feel a force. Well, it'll feel the force due to that acceleration. Whether it accelerates toward the other mass depends what other forces might be acting on it. Okay, we're going to use the flux model first, then we're going to use Newton's model. Now, we calculate the flux of the 100-gram mass. Okay, that's 4 pi times big G times the mass. The mass is 100 grams or 0.1 kilograms. We multiply these out, we get a flux of about 8.4 times 10 to the negative 11th Newton meter squared per kilogram. Now that flux is spread out over the area of a sphere with a radius of 3 centimeters. Well, the sphere area is going to be 4 pi r squared, that's the area of a sphere. R is 0.03 meters, so we end up with this expression, which we easily put into a calculator and get approximately 0.0113 square meters. Then we calculate the gravitational field. The gravitational field is the flux per unit area, so we divide the flux by the area. The flux of 8.4 times 10 to the negative 11th Newton meter squared per kilogram squared by the area, 0.0113 meters squared. And we note that a Newton meter squared per kilogram is a meter cubed per second squared. You'll get that very easily if you remember that a Newton is a kilogram meter per second squared. So it's substitute kilogram meter per second squared for Newton. Kilogram will divide the kilogram and you'll end up with meter cubed over second squared. We divide this by the area, again, in square meters, and the meter cubed will be divided by the meter squared and just give us a meter. And we'll end up with a gravitational field of 7.4 times 10 to the negative 9th meters per second squared. And that is the gravitational field strength, or the acceleration that an object feels at a 3 centimeter distance from a 100 gram mass. It follows from this that, of course, okay, as we stated, the 70 kilogram mass accelerates toward the 100 kilogram at this rate. That is, if it's left free. Otherwise, it just experiences that as a force. But the point is that in either case, the force it experiences is its mass, which is 0.07 kilograms, times that gravitational acceleration. Not the gravitational acceleration, but that gravitational acceleration in this situation, which is 7.4 times 10 to the negative 9th meters per second squared, giving us a force of 5.2 times 10 to the negative 10th newtons. And that's a force that we get using the flux model. Now we can easily get the force if we simply multiply if we simply use Newton's law of universal gravitation in its original form. Maybe it's original, maybe it was stated in a slightly different form, but this is pretty close to the original form. I wasn't there, so I'm not sure exactly what he said, but it's pretty close to this. Okay, so M1 is, let's say, our 100 gram mass, M2 is our 70 gram mass, R is the 3 centimeter distance between their centers, G is the universal gravitational constant. We just plug the numbers in and chug them out, and we get 5.2 times 10 to the negative 10th newtons, which is exactly what we got from the flux model. Now what if we had started with Newton's model rather than the flux model? They're equivalent, we've said that. Let's just get an idea, let's make it real clear that these things are equivalent. Okay? So let's take this force, actually the acceleration, let's take this force and calculate the acceleration that the 70 kilogram mass would experience if it was free to accelerate. Well, that would be force over mass, and what's that turn out to be? 7.4 times 10 to the negative 11th meters per second squared. Now, I think maybe there's an error here because it was 10 to the negative 9th meters per second squared. So that 11 is incorrect. Let's kind of put an X through that. You need to make a note that that's a ninth. I think that's noted in your materials. Now, knowing the gravitational field to be 7.4 times 10 to the negative 9th meters per second squared, we can calculate the flux. We've got g, our acceleration. We can find the area of the sphere and multiply it by the gravitational field, and we're going to get the flux. Well, the area is, as before, 0.0113 square meters, which implies the gravitational flux is our 7.4 times 10 to the negative 9th meters per second squared, it should be, multiplied by 0.0113 square meters. And when we get done multiplying that, we do end up with 8.4 times 10 to the negative 9th meters cubed per second squared, which was the total flux that we obtained before. So you see, we can start with Newton's formulation and obtain the flux picture, or we can start with the flux picture and obtain the same thing we obtained with Newton's formulation. They're equivalent. It doesn't matter which one we use, but we need to understand them both.